So I thought I'd just fill in a little bit of the blanks from the last video, and just cover a little bit more about why Russell's paradox was seen as such a major thing, and why Frege would go into this deep depression when he heard about Russell's paradox, because on the surface it would seem that Russell's paradox isn't such an enormous thing. I mean, after all, it's paradoxes were nothing new. I mean, paradoxes have been used in philosophy since forever, and some paradoxes, like Zeno's paradox, sort of seem to have a quite a straightforward, almost empirical solution. So Zeno's paradox, if one recalls, is where you have an archer that fires an arrow, and before the arrow reaches its destination, it must cover half the distance, and then it has to cover half of the distance, and then half of the half of the half, and so forth. And so if one sort of works it out mathematically, you would see that the arrow would never reach the target, because the gap would just keep getting smaller infinitely, but it would never actually reach the target. And but of course, in practice, the arrow does reach its target. So it turns out, well, maybe it's not such a big deal. And this is one of the sort of hints that mathematics may not be equivalent to logic always. But be that as it may, there's lots of paradoxes like that. But Russell's paradox falls into a sort of a different kind of category. And if we recall, Russell's paradox was the set of all sets that don't contain themselves. But it also gives a general form for a certain type of paradox that can't be resolved in that sort of way. So if one thinks of the barber's paradox as one specific example of that, where does the barber who doesn't shave himself? It's just like, I keep getting this wrong. Does the barber who shaves everybody who doesn't shave themselves shave himself? And so we can think of Descartes' cogito ergo sum as also falling into this category, where one can say the set of all thoughts that are not thoughts cannot exist. Essentially, is one way of thinking of it. Because cogito ergo sum sort of really stands sort of at the beginning of modern thought, of the Enlightenment era. Those sort of paradoxes have a kind of a special place. But the real reason why this kind of became maybe more important towards the end of the 19th century, specifically, when Russell was working with Frege on this sort of set theoretic. Well, I don't know how closely they were working, but at least they were in collaboration. That's why Frege heard about Russell's paradox. But this was sort of getting to the end of the 19th century, and trying to set mathematics on this sort of set theoretic basis. So just to help understand why Russell's paradox was so devastating, it's helpful just to take a little step back and just look at some of the other mathematical developments in the late 19th century. And the two really important ones that I just wanted to discuss in this video is the Dedekind cut and Cantor's diagonalization, if I can say that properly. And so together, these two kind of give the context as to why that set theoretic thing was maybe thought to be like a solution to a very big problem. So firstly, if we just look at the Dedekind cut, essentially the problem came in with the specific type of number, the irrational numbers or transcendental. Well, irrational numbers, and there's a class of irrational numbers, the transcendental numbers. now these are the sorts of numbers that have these infinite. They can't be written down finitely. So the classic examples of these are the transcendental numbers pi and e, which are of course really important. And so it would be kind of helpful to understand how those numbers fit into the general sort of context of reals, of rational numbers. Rational numbers being numbers, one number divided by another, or natural numbers. And so a good starting point is just to think that when you think of natural numbers like 1, 2, 3, and you think of integers like minus 1, 2, 3, and you think of rational numbers, these numbers you can enumerate. So they're finitely enumerable. So what that means is that even though there's an infinite number of them, you can assign on a one-for-one basis. Each time you add a new number, you have another natural number that you can assign to it. So because infinity isn't a number, it's sort of a concept. It's sort of a concept of never ending. Well, the integers are never ending in the same sense as the natural numbers are never ending, in the same sense as the rational numbers are never ending. So that's fine, but the problem is where the irrational numbers fit into this, and essentially the problem sort of comes up where if you take a real number line, the irrational number line, the irrational numbers kind of form these sort of gaps in the number line. So they sort of like almost breaks in the rational number line. So between the rational numbers, of which the natural numbers are obviously also rational numbers. So in between the rational numbers, there's these gaps made up by the irrational numbers. So what we want to know is we want to know how big those gaps are in relation to our numbers that we can deal with finitely. So that we want to know, like, okay, we know about numbers like e and pi. Okay, that's fine. But how many of those are there? And what is the proportion of those kind of numbers to the ones that we normally deal with? And that's kind of important because that would help us understand just how many of the numbers we know, kind of thing, in a way. So if we want to establish the logical basis for mathematics, there needs to be something we can hold on to there. So essentially, this is where Dedekinds cut kind of comes in. Is where he was saying that, well, if you even though you can't finitely represent one of these irrational numbers, you can pinpoint it or arbitrarily get close to it by saying that all of these rational numbers are bigger than it, or smaller than it, and all of these rational numbers are bigger than it. So you can make a cut, and you can arbitrarily get close to that number, sort of hone in on it, by sort of defining what's larger and what's smaller, and your irrational number will be the one in the middle there. So when you think of it that way, it looks like, okay, our irrational numbers, they're going to be like vanishing. They're just going to be these sort of like vanishing pinpoints on the real number line that we can essentially, we can find one or two of them, and then it's fine. We can kind of ignore the rest. They're kind of like these sort of infinitesimal little dots in the real number line. And so this is where Cantor's diagonalization kind of came in and threw a spanner in the works, because what he did was he said, okay, if you've got an infinite list of irrational numbers, and you enumerate them, just as like you would do with the natural numbers, with the counting numbers. The problem is that because these numbers have a infinite extension, you can take the first number of the first of your irrational numbers, and the second digit of your second one, the third digit of the third one, or the fourth digit, and all the way you can carry on infinitely with each digit like that. So even though you've got an infinite list of these irrational numbers, you haven't captured all the irrational numbers. So in other words, there's more than so you take each one of those digits and you change them by one. So you change the first digit by one, change the second digit by one, and each digit in succession like that. And so now you end up with a number that's different from the first number in the first digit, different from the second number in the second digit, different from the third number in this third digit, and so forth down to infinity. And so you end up, by construction, you end up with a number that's not in your infinite list. So you've got more than infinite irrational numbers. So if we go back to the number line, this becomes a problem, because what this essentially means is that your irrational numbers are what you can think of it like as a second order of infinity. So there's more irrational numbers and infinitely more irrational numbers than there are rational numbers, than there are other sorts of real numbers. So even though your list of real numbers is a continuum, when you add in these irrational numbers, the space taken up by our sort of tractable rational numbers is infinitely small. So in fact, what you have this number line that's almost all entirely empty space, made up of numbers that you cannot write down, that you can't define. We know one or two of them, e or pi, but most of them are, and all of these numbers that we can think of, like 1 and a half and things like, all of these numbers are infinitesimally small on the number line. So they take up no space effectively on the number line. So in other words, we effectively know almost none of the numbers. So this is kind of problematic when we sort of wanting to establish mathematics as the basis for logic. And so this sort of gives an insight into why this sort of set theoretic way of looking at the world, of making cuts in the world, was a very attractive way, because if we can establish mathematics on the basis of these kind of cuts, and not having to deal with real objects, where we have to assign a number and a truth value to a thing in the world, then that would solve it, because now we could use Dedekind cuts instead of assigning values to if we use the example of a puddle of water. You have one puddle of water and one puddle of water, and you put them together, you get one puddle of water. So 1 plus 1 only works for certain sorts of things in the world. So 1 plus 1 equals 2 is a statement about the world. It's not a purely logical mathematical statement. And that has profound consequences for the logical basis of mathematics, because logic doesn't accept that sort of thing. If you make a logical statement, it must be true for everything. If 1 plus 1 equals 2 isn't true for everything, it ain't logical. So you can't have it both ways. So that's really important to bear in mind. So if one could establish mathematics on the basis of set theory, on the basis of these cuts of the world, well, that would be great. Except you can't, because of Russell's paradox. And that's essentially why it was such a devastating discovery, almost. Even though sort of in the abstract it might seem, yeah. If one sees it in the context of the greater project of the Enlightenment and the industrial era, it takes on a much more dramatic sort of role. So yes, I think I'll leave it there. But in the following videos, I'm gonna just try and now just have a look and see some of the sort of responses to this sort of turn of events. and see where we go from here. So, but we'll leave it there for tonight. So have a good one.